In this video, I would like to demonstrate a proof for the law of cosines. And recall that the law of cosines can be written in terms of any relationship between an angle and its two adjacent sides and the the length of the side opposite. So in this case, we can relate A, C, and B to the side little c. This proof is going to be done based on this orientation of the triangle, but it would follow similarly for angle B and angle A. All I have to do is place the angle that I would like to use as the law of cosines formula at the origin. So to do this, I want you to place this triangle. We're going to place it on the rectangular coordinate system. So this is my x-axis and this is my y-axis. What are the coordinates of this point right here? We'll recognize that if I create this triangle by dropping a side straight down, so I have a right triangle here whose angle inside is capital C. I know just from the fact of the definition of trigonometric functions that the coordinates of this point here would be a cosine of capital C, comma, a sine of capital C. Now, why is that the case? It's because if you think of it as this point is on the outside of a circle whose radius is A, then the coordinates of where that angle intersects a circle of radius A is A cosine C, A sine of C. You can also look at it in terms of this side here, X, and this side here, Y. We could write down saying that the sine, no, I will do cosine. Cosine of C is adjacent over hypotenuse, so X over A, which means X would be equal to A cosine of C, which is exactly what I have as the X coordinate. Similarly, sine of C would be Y over A, which means Y is A sine of C, which is what we have right there. So that's where we get the coordinates for this point. Now recall that the distance formula between any two points can be calculated as the difference in the x coordinates squared plus the difference in the y coordinates squared, all taking the square root up. Or d squared is x2 minus x1 squared plus y2 minus y1 squared. So I want to use the distance formula for the distance between this point here and this point here. Now the coordinates of this point are clearly b for x and 0 for y, because it does not go above or below the x-axis. So then, the distance from point B up here to point A down here, that is the point at angle B and the point at angle A, we know is C. So I'm going to use this formula right here, and I'm going to say I know the distance between those 2 points is C. So using that second formula, C squared would be equal to, not square root, sorry, I don't know why I put that there, the difference of the x coordinates. So we take the x coordinate of this point, which is B, minus the x coordinate of the point at the top of the triangle, which is A cosine of capital C squared, plus now the difference of the y coordinate, so 0 minus A sine of capital C squared. And the rest is algebra. If I multiply these out using FOIL, this becomes B squared minus a 2AB cosine of C, that's twice the product of the first and last term, plus an A squared cosine squared of capital C, plus, and now a square of this minus is going to become a positive, so you just get A squared sine squared of C. Now notice that these two terms here have in common an A squared. So you have B squared minus 2AB cosine of C plus a squared times cosine squared of c plus sine squared of c. And by the Pythagorean identity, that is always equal to 1. So just moving the a squared to the front, I have a squared plus b squared minus 2ab cosine of c. And as we said, that's equal to c squared. That is the law of cosines. And that would hold for any angle. All you have to do to solve it or create the law of cosines for angle B would be to rotate your triangle around and start from there. But it would work the same way for any of your angles. So that's the proof of the law of cosines.